Ever cracked an ice cube tray after forgetting it in the freezer too long? It happens. Ever cracked an ice cube tray after forgetting it in the freezer too long? It happens.
Happens to the best of us.
But did you know that same kind of pressure, that cryosuction as it's called, can wreak havoc on buildings and roads, all thanks to the soil beneath them?
Exactly. And what's fascinating is we often think of frozen ground as just, well, solid. But it's really this dynamic system way more complex than just ice cubes.
Okay, so walk us through it. What's really going on down there when the temperature drops and the earth starts to freeze?
So picture this. You've got the solid particles of the soil itself, right?
Right.
Then you've got water hanging out in the spaces between those particles.
Makes sense.
Now, as things get cold and ice crystals begin to form, they need space to grow.
Just like that ice cube tray overflowing in my freezer.
Precisely. And those growing ice crystals, they don't just sit politely where they formed, they actually draw in more water from their surroundings.
Huh?
And as they grow, they exert this incredible pressure on the soil around them. That's the cryosuction in action.
So it's not just the expansion of water freezing like we learned in school. There's more to it.
Right. It's the combination of the freezing process, AND, this movement of water, all driven by the density difference between water and ice. You see, ice is less dense than water, which is why it floats. But in soil, this density difference creates a sort of tug of war, pulling in water as those ice lenses form and expand.
Okay, I'm starting to see why this isn't as simple as a frozen puddle. We got these ice lenses you mentioned. They sound important.
They are. Think of them as thin layers of ice, almost like tiny frozen pancakes forming within the soil. And these ice lenses, they're the main players when it comes to that cryosuction. As they grow, they push apart soil particles, and that's where the real pressure comes from. And it's not just theoretical, this pressure is a major engineering concern.
Okay, now we're talking. So how do scientists even begin to wrap their heads around this whole process? I imagine there's some serious math involved.
You're absolutely right. To understand, and more importantly, to predict how freezing soil will behave, scientists use these intricate equations, and these equations factor in a whole bunch of variables.
And when you say intricate, what are we talking about? I'm picturing pages full of Greek symbols.
Well, there are definitely a few of those. But to give you an example, one of the key things these equations look at is the porosity of the soil. Basically, how much space there is between those soil particles. The more porous the soil, the more space there is for those ice lenses to form and grow, which can lead to even greater cryosuction.
So it's like the more porous the soil, the more dramatic the effects of the freezing.
You got it. And these equations, they don't just look at the soil itself, they also take into account things like the temperature gradient, how quickly the temperature changes from the surface down, and of course, the availability of water in the soil.
It's amazing how much complexity there is in something we often just walk over without a second thought.
It really is. And this is just the beginning. We've talked about the forces at play, but what about the structure of it all? How do those ice lenses actually form and arrange themselves within the soil? It's pretty wild, and we'll dive into that right after this.
Okay, so we've established that under the surface, it's a whole frozen world down there. What I'm curious about is how researchers actually see these ice lenses forming. I mean, they're underground, right? It's not like we can just pop open the soil and take a peek.
You're right, not quite that simple. But researchers have gotten incredibly good at visualizing this hidden world.
Okay.
They use X-ray scanners, similar to the ones in hospitals, but often even more powerful to capture images of the soil as it freezes.
Wait, hold on. They can actually watch these ice lenses form in real time using X-rays.
It is incredible, and the images they get are amazing. You can literally see the water being drawn toward the freezing front, crystallizing into these distinct layers, forming those icy pancakes we were talking about.
So it's like watching a microscopic winter wonderland unfold. But instead of snowflakes, it's these ice lenses taking shape.
Exactly. And this technology isn't just about pretty pictures. It allows researchers to study the formation of ice lenses in incredible detail. They can see how the size and orientation of the ice lenses change depending on the type of soil, the temperature, even the speed at which the soil is freezing.
So this is where those complex equations we talked about earlier come into play, right? Helping make sense of all this.
Absolutely. Those equations help researchers interpret those X-ray images and understand the forces driving those patterns. For instance, they found that the ice lenses don't just form randomly anywhere.
Oh, really?
They tend to align themselves perpendicular to the direction of heat flow.
Okay, so if the cold is coming from above, these ice lenses are forming horizontally, almost like a shield against the frost.
That's a great way to put it. And that alignment, that structure, It's a big part of what makes predicting the behavior of freezing soil so complex, because it's not just about how much ice forms, but how those ice lenses are arranged within the soil.
So it's like a microscopic architectural marvel down there.
Precisely. And just like a building structure determines its strength and stability, the arrangement of these ice lenses has a huge impact on how the soil behaves when it freezes and thaws.
This is all fascinating, but I have to ask, what does this mean for us on the surface? How does understanding these tiny ice lenses translate into real-world applications?
It's all connected. Remember how we talked about cryosuction and the pressure it exerts?
Oh, yeah.
Yeah.
That was kind of terrifying, actually, imagining things spontaneously erupting from the force of ice.
Exactly. And it's not just sidewalks, it's roads, buildings, pipelines. Anything built in cold regions has to contend with this incredible force.
Right.
So understanding how these ice lenses form and how their arrangement affects the overall pressure exerted on structures is crucial for designing infrastructure that can withstand these forces.
So it's not just about predicting whether a sidewalk will heave a bit in the winter. It's about building structures that won't crumble under the pressure.
Precisely. And it goes even further than that. Understanding these microscale processes, those ice lenses and their behavior, can help us predict not just frost heave, but also thaw settlement, that sinking feeling you get when the ground thaws and the ice lenses melt away.
So the formation and melting of these tiny ice crystals can have a ripple effect on the entire landscape.
Exactly. And this isn't just about buildings and roads. It's about understanding the long-term impact of freeze-thaw cycles on soil properties, which has implications for agriculture, ecology, even the climate.
Wow. So this is way more than I ever imagined.
Yeah.
But you mentioned something earlier that piqued my interest, this idea that the ice itself in soil is different. You said it doesn't behave like the ice we're used to. What did you mean by that?
Right. So far, we've been focusing on how ice forms and organizes itself in soil. But what's truly remarkable is that the properties of ice itself change when it's confined within soil. Remember that ice cube analogy?
Yeah.
We think of ice as being uniform, but in soil, it behaves in a much more complex way.
Okay, now I'm really curious. Tell me more. Okay, so you're saying the ice itself is different in soil. That's wild. I thought ice was, well, just ice. What makes it so different down there?
It all comes down to a fascinating concept called anisotropy. Think about that ice cube we talked about.
Okay.
It's the same in every direction, right? You could spin it around, look at it from any angle, and its properties wouldn't change. But ice in soil, because of the way it forms within that confined space and the influence of those ice lenses, well, it doesn't behave that way.
So it's like a frozen jigsaw puzzle, where the pieces can only fit together in very specific ways.
That's a great way to think about it. And that specific way has a big impact. For example, frozen soil might be much stronger in one direction than another, almost like a bundle of straws frozen together. Strong along the length, but pushed from the side and...
Total frosty disaster.
Exactly. And it's not just strength. Even things like how heat travels through the soil or how much the soil expands and contracts with temperature changes, all of that is affected by the anisotropic nature of the ice within it.
Okay, now I'm starting to understand why understanding these tiny ice crystals is so important. But how do researchers even begin to study something as complex as anisotropic ice? And what are the real-world implications of all this? I mean, we've talked about cracked sidewalks and such, but this seems like it goes even deeper than that.
You're absolutely right. It does go much deeper. Anisotropy has huge implications for everything from the stability of slopes to the design of foundations in permafrost regions. Imagine building a massive structure on ground that's stronger in one direction than another.
Yeah.
You'd need to factor that anisotropy into your design or risk some serious structural issues down the line.
That makes perfect sense. And I imagine researchers have to get pretty creative to study and model something this complex.
They do. It involves a combination of sophisticated lab experiments where they can control things like temperature gradients and soil composition, along with advanced computer modeling. The researchers behind the papers we're looking at have developed these incredibly detailed models that can actually predict how anisotropic ice will form and behave under different conditions. They're essentially creating virtual versions of the freezing soil to test different scenarios.
So they can see how changing even one variable, like the type of soil or the rate of freezing, might affect the anisotropy of the ice and ultimately the strength and behavior of the frozen ground.
Exactly. And this kind of predictive power is invaluable. It allows engineers to design structures that are specifically adapted to the unique challenges of building on permafrost or in areas with seasonally frozen ground.
It's amazing to think that something as seemingly simple as ice can be so complex and have such far-reaching impacts.
It really is. And that's just it. We often think of ice as this static, unchanging thing. But when it comes to frozen soil, nothing could be further from the truth. It's dynamic, it's complex, and it plays a crucial role in shaping the world around us.
This has been a fascinating deep dive, to say the least. We've gone from basic concepts like cryosuction to the mind-boggling world of anisotropic ice. And it's clear that there's still so much more to learn and discover about this hidden realm beneath our feet. So, as we wrap up, what's one key takeaway you hope our listeners will walk away with today?
I think the biggest takeaway is that the world beneath our feet is far more dynamic and complex than we often give it credit for. Freezing soil isn't just about water turning into ice, it's about this intricate dance of phase transitions, the surprising power of microscopic structures, and the unique properties of materials we think we understand, but which can behave in unexpected ways depending on their environment.
It's a reminder that even in seemingly simple things, there's often a universe of complexity waiting to be discovered.
Precisely. And that complexity is not just intellectually stimulating, it has very real implications for how we design and build in a world facing a changing climate.
Absolutely. And on that note, we'll leave you with this thought. If the type of soil and the speed of freezing can influence how ice forms, what other factors, perhaps things like the presence of pollutants or even microbial life in the soil, might be playing a role in this